Hello! In this video I'm going to take you through some of the fun features of DerpCAM. For anyone that's interested in a quick overview of DerpCAM, I encourage you to look at my previous video, An Introduction to DerpCAM. So, first of all, let's load some geometry. I'll import this file. There we are, little dinosaur in an egg. So, let's talk about pocket operations first. Let's presume that we want to mill out the inside of this egg shape. I'm going to click on here. Actually, before I do anything, let me go to Workpiece and set the material. Let's cut this out of wood. This will give us a set of sensible defaults for all the operations. Okay, let's select the egg, machining, pocket, and let's select an end mill. So this operation is trying to cut out everything inside, on the inside of this egg shape. It picks a summary of the egg shape and spirals on out. That's fine for a nice simple shape like this, but what if we want to leave the dinosaur uncut? So if we go to Islands, select that, apply. So there I went to the Islands menu of the operation. Okay, you can see the DerpCAM's done more or less the right thing. It's identified that there's going to be 3 pocket shapes, but it hasn't done a very good job of, the default algorithm hasn't done a very good job of clearing that. It's, the default algorithm just really isn't aware of this dinosaur shape in the middle. So let's play with a few different strategies. So that was using the contour parallel strategy. I advise you to have a play with this arc peel strategy. The difference in arc peel with zigzag and regular arc peel I'll get to in a moment. For the moment, let's go with zigzag. Whoops. So you can see it's now doing a much better job of this. It's identifying the largest fit circle, drawing a spiral to that, and then it's progressing down the empty space with these arc shapes. Now, the thing about these arc shapes that might not be immediately apparent is that they meet the edge of the pocket at a tangent to the edge of the pocket. What do I mean by that? If you zoom in, you see that the end of these arcs is actually parallel to the side of the pocket. So this is great for tool life. This means you're never changing the direction of motion through the material quickly. It's a nice even pressure at all times. You're never running the tool straight into an edge and stopping quickly. As this algorithm goes up into tighter corners, it can no longer step by the same regular amount as it becomes more and more constrained. Like chips are going to bog down the end mill and things like that. So it just starts taking thinner and thinner slices. Now, it's taking lots of individual slices here. They get really, really small, but these are all very small movements. They don't actually take that long. I advise you to have a play with this algorithm. Works very, very well. I'm biased. I wrote all the code for this, so I find it interesting and fun. I hope you do too. So, onto the with zigzag. So, if you know anything about CNC operations, there is conventional milling, there's climb milling. One goes one direction, the other goes the other. Here, for each of these arcs, when we get to the far end, because we've got with zigzag enabled, rather than retreating back across the material and starting another arc just ahead of where we started the previous one, when we get to the side, we actually reverse the direction and come back again. So this means a lot less, like the machine's doing a lot less movements, individual movements, but it is breaking the conventional or climb setting here. It's not obeying the conventional or climb setting. That may be acceptable to you, it may not. It probably depends what it is you're machining and how rigid your machine is. Let's just so you can see what I'm talking about, switch to just the regular HSM algorithm. Yeah, okay, here you can see the machine is taking a slice and then coming back across to close to where it started the last arc, before making another one. Cool. Let's delete that operation and try something else. Okay, let's pretend that we want to cut this dinosaur out of a piece of regular stock, leaving the dinosaur behind, but like thinning the regular stock, so it kind of leaves the dinosaur embossed, if you like, sticking out, like sticking out above the base level of the stock. So here we can use the very basic CAD functionality in DerpCAM. Let's draw a rectangle. Okay, didn't get that in exactly the right place. Need input for this. Double click on that. And now I can just drag those. Okay, let's apply that. Okay, here we've already got the rectangle selected. Machining, outside peel. Let's use the same end mill as last time. Okay, this is worth mentioning just while we see it. See this top line, cutters in project, and there's a cutters in global inventory. Cutters in project is any end mill, either any tool or any preset that you've already used in this part so far. The mentality here is, if you were to save the project, export it from this computer and load it on another computer that doesn't have the same set of cutters and presets in global inventory, you're gonna have a problem. So DerpCAM actually exports any cutter or preset that you've used within the project with the project itself. So here, let's go with the one that we're already using in this project. Okay, so what's this doing? Let's assume that the rectangle was the edge of our material. This has just started, roughing out the whole surface. We want to leave the dinosaur shape. So this is quite simple. Excuse me. This is quite similar to the last operation we did. We want to change the strategy. Again, I'm going to use arc peel, and I'm going to use arc peel with zigzag because it's just easier to visualize here. Okay, so this now starts off in a corner and starts drawing arcs all the way across the material. Let's leave the dinosaur as an island and apply that. Okay, so starting at the same place, it progressively draws a larger and larger circle until it gets to the part, and then it picks a direction to start drawing the arcs. You notice the edge of the arc at the dinosaurs are doing this. At the dinosaur is doing the same thing I mentioned earlier. It's coinciding with the edge of the shape at a very shallow angle, sort of like relieving tool pressure. Actually, on the edge of the material, it doesn't matter. This is the edge of the material. It really doesn't matter what it does here. It can afford to just run off the material, in whatever way is most time efficient. This does actually give you a good view of what the with zigzag is doing. It's drawing an arc out this way, and then it immediately travels to the start of the next arc, rather than traversing, like back to the start of where the previous arc went. Okay. What else can we look at here? So you will notice there's a line a line parallel to the edge of the part. This is actually a cleanup pass. After DerpCAM finishes doing the one of the HSM operations, it actually runs the end mill all the way around the edge just to tidy up any of these little loose triangles. Things much smaller than the minimum step over size of the algorithm. You will notice that occasionally the algorithm does just slightly overlap this finish pass. If you're looking like this algorithm, it's great for roughing out big areas, but if you're looking for a smooth finish, you want to set this offset running. Excuse me. You want to set this roughing offset to some relatively small value. Let's go with 0.3 millimeters there. Now you can see the finish pass is still in the same place, but the actual roughing operation that takes out the vast majority of the material doesn't actually come all the way up to the final line. It leaves a small uneven path around the edge, which DerpCAM will run an end mill all the way around and just give this a much nicer, cleaner finish. Okay. Let's get rid of that. So what if you wanted to just cut out this dinosaur shape? Because who doesn't want a little dinosaur shape? So you're going to want to offset the end mill to the outside of the line by the radius of the end mill, and then just follow along parallel to the line all the way around. Sort of following a contour, if you like. The operation for that, click on dinosaur shape, is outside contour. Let's click on that. Select an end mill. And simple as that. We're done. Let's have a little look at what's actually happened there. So we're cutting to full depth here. What is full depth? If we go to the workpiece, this is the material we're cutting things out of, it's set to 15 millimeters thick. So the operation full depth is going to default to that 15 millimeters. If we want to set it to something less, we can do that. So the end mill isn't going to cut the full 10 millimeters all at once. The end mill is going to look at this cut depth per pass figure. So this 1.5 millimeters, this is DerpCAM's default based on the material type, which again was set here under our workpiece, wood in this case, and the end mill. It's going to, DerpCAM knows a little bit about materials and end mills, and for the end mill we've selected, it's decided that 1.5 millimeters per pass is a good depth. If you know your machine better, you might want to override this. So you can either do that here directly, set that to 2 millimeters or something, or you could go and choose a preset, as we've discussed earlier. If you do choose a preset, you can select which preset you want here. Okay. Let's look a little closer. So what's actually happening here? DerpCAM is sort of like pushing the end mill down to the 2 millimeter depth that I've selected here, and then it's starting to push it through the material. So, like along this line. So the most pressure is going to be on the leading edge of the end mill, right? That's what's pushing into the material. The end mill is rotating and it's throwing chips sort of back into the slot. Problem is, some of these chips aren't going to be sitting exactly in the flute. Some of them are going to be on the side of the end mill, some of them are going to be on the side of the pocket. So some of them are going to try and jam this end mill into the slot we're drilling. This kind of operation is called slot milling. It's particularly tricky with like soft metals like aluminium or plastics, where you're continually recutting chips. Is going to cause those chips to heat up and eventually melt. And once they melt, they're going to stick to the side of the slot, they're going to stick to your end mill, and just generally bad things will happen. So This isn't really ideal. I mean, even if you're cutting material that isn't prone to melting or burning, it's still causing more stress for the end mill. So what can we do about that? You notice here there is an extra width setting. If we set that to 50%, you can see we've increased the width of the slot. The edge of the slot is still right at the edge of the part. The end mill isn't overlapping the part. The extra width has gone on the outside of the part. So now the end mill is going to be pushing along here at its 2mm in this case depth, and it's still going to be slot milling at the moment. It's basically going to go all the way around the part until it comes back to here. At this point it'll then traverse over to the other line and now widen that slot. So it's going to be doing this first of all next to the part, so hopefully the finish right up against the part is going to be increased because the end mill isn't under the same stress, and it's going to go all the way around the part until it gets back to here, at which point it's going to traverse back to this side, push another 2mm down, and this time we're slot milling again, but the bottom of the end mill is now 4mm below the surface and the slot's only 2mm deep. So it's not nearly as bad as when we were just pushing round and round in the same slot. But it's still not perfect, right? Is there anything we can do better? And yes, there is. This trichoid setting, this refers to trichoidal milling. If we set this to some value other than 0, let's give it 30%. Now this is going to take a little time. You'll see why in a second. It's actually doing quite a lot of work here behind the scenes. And there we are. So the slot is still the 50% wider, but now instead of just pushing a straight line, the end mill is drawing lots and lots of little spirals. Like intuitively you can see why this is, this is going to prevent the end mill getting jammed in a slot, but it's a much longer path, right? So intuitively you might think that this is going to take a lot longer. Well, you can actually run with a much higher feed rate if you're trichoidal milling like this than you would if you were just slot milling. As long as your machine is reasonably stiff, you should be able to go at least as fast as you would slot milling, but a lot more reliably. You're not going to be prone to the same, like random tool damage and things like that. I will say if your CNC machine isn't particularly stiff, drawing lots and lots of little circles like this is going to add vibration. So you are going to want a fairly stiff machine before you get the best out of a tactic like this. But even if you don't, I would advise you just play with it. See, see, does it increase your performance? Does it increase your reliability? As a hobbyist, I'm really more interested in reliability than speed. I'm not trying to beat any records on how many parts I can send out of my factory. I'm usually just making 1 or 2 of something. So I'm more interested in reliability and not breaking my inexpensive end mills. And yeah, that's about it. So I hope you found this enjoyable or interesting or a bit of both. And yeah, thanks for watching. If you give DerpCAM a go, let us know how you got on. If you have any questions, send them my way, and we'll see if we can work out an answer for you. Cool. Thanks. Bye.